on advances in experimental therapeutics. We have an engaging lineup of lectures and tutorials today by our esteemed speakers. Let's dive right into today's schedule. To begin with, we have Dr. Aman Bhalla, who will be delivering the lecture in our series titled Asymmetric Synthesis in Drug Design, Need and Basis. Dr. Bhalla has been guiding us through the crucial strategies of chirality and selectivity in drug development. We are eager to continue this journey with him. Let's welcome Dr. Bhalla with a round of applause.
A very good morning to all present. Okay. So yesterday we have started the asymmetric synthesis in drug and designing. That what is the need of the asymmetric synthesis. Okay. So we are continuing with that part, and as I said in our previous lecture, that this topic is selected so that you are able to get the hints, you are able to get that what type of synthesis you have to plan so that you get your desired compound in a high enantiomeric purity, so that the beneficial effects of particular isomers can be taken into the next steps. So as I said earlier, that if you have a one or the two enantiomer in your synthesis, you have to purify them, you have to characterize them, you have to give the data of both the enantiomer in the market, then it will be approved for further use. Okay. So we move to the next, which is the most important slide if you have to study about the asymmetric synthesis. Okay. That is the selective synthesis of enantiomers. Okay. If you see the reaction, which that is a very simple reaction, can you see what is in your substrate? It is a simple aromatic ring and the carbonyl functionality. It is not any complicated reaction scheme. You just see in your substrate it is a achiral. Okay. Now if you see the final products, you are getting the reduction of the carbonyl compound, you are getting the corresponding alcohol molecules. But if we are talking about our substrate, that is carbonyl compound, it is planar in nature, it has sp2 hybridization. So if you try to add any group on it, it has a possibility that that group can either attack from the upper plane or it can attack from the below plane. Okay. So in a simple reaction, if I show this is the carbonyl group and you are adding hydride ion on it, the hydride ion can attack from the upper plane or it can attack from the lower plane. That means you have a 50-50% chances. So I just quote a very simple example. We are sitting in this room. Okay. If 100 students are coming into this seminar room, we have two doors. 50 students can come from back side, 50 students can come from front side. This is the possibility which we can execute. But if we close either of the door, if we close the backward one or the front one, then what is the possibility? Only from the one side. Okay. So what is asymmetric synthesis? It is the synthesis in which a chiral unit, which is the ensemble of your substrate molecule. What is a chiral unit? If you see, there is only aromatic ring and the carbonyl group. So that is a chiral unit is converted into a chiral unit in a such a way that the possible stereoisomers are formed in unequal amounts. So this is your asymmetry. Okay. Now if you see, you are getting two enantiomer, that is S or R. But what we have written below, that is non-racemic, unequal mixture. Okay. So how you planned such type of synthesis where the possibility generally is 50-50, but you are forcing the reaction that this possibility should be unequal. If it is unequal, then your asymmetric synthesis is going to start. Okay. So it is a desired proportion, that the enantiomer which you desired for your final target. What is your final target? You want an antibacterial molecule, antioxidant, anti-cancer, antiviral, whatever the property you are desiring. Okay. So that's why either you get A or either you get B. Now I am just asking, what is the difference between A and B? It is only the stereochemistry, the arrangement of hydrogen and OH in the three-dimensional space. In first picture, that is hydrogen is below the plane. In second molecule, the hydrogen is above the plane. So this is the only difference, but you want such molecule in unequal amount. So which enantiomer is more preferable as compared to the other one, that tell you the enantio selectivity. So if you see yesterday lecture of Professor Narinder Singh, there are number of molecules which have a chiral unit. If you present any molecule in your studies and say that my molecule is in chiral, the first question of the reviewer is that what is the enantio selectivity and what is the diastereoselectivity. You cannot just put the chirality and you say that I have prepared it. Nobody is going to take this, you know, because yesterday we discussed the thalidomide case. Everybody wants that if it is a chiral molecule, you have to report the enantio selectivity or the diastereoselectivity of such molecule. So that means you have to get the proportions, that which enantiomer is in majority and which enantiomer is in minority. So if you plan a synthesis and the synthesis works, and if you are getting A and B in the 50-50 ratio, then you say your reaction giving racemic product, because both the enantiomers are in 50-50%. But if you see the percentage, your A is 90 and B is 10. That means how much is the excess of A with respect to B? That is 80. If A you get 90 and B you get 10, then what is the excess? 80. So that is your 80% excess of one enantiomer over the other. But if you perform a reaction in which A is 100% and B is 0, okay, then your one enantiomer is formed in a 100%, other is out of this system. So what you call, if you get only one enantiomer, that is your enantio specific reaction. But if you get the enantiomeric, if one is 90, other is 10, then you call it is a enantio selective reaction. So when any chiral reaction is going to perform, you have to explain in such type of terminology. The reviewer or the judge or the interview panel expert, whenever you are presenting your work to them, they going to ask, is your reaction enantio specific or enantio selective? Then you have to say that if you get only one type of enantiomer, your reaction is enantio specific. But if the ratio is 90-10, 80-20, 70-30, then you say that my one of the enantiomer is in excess as compared to the other. So that is enantio selective reaction. So in asymmetric synthesis, this terminology is required because whenever you are going to see the asymmetric aldol reaction, asymmetric Diels-Alder reaction, asymmetric Sharpless epoxidation, hydroxylation, every time the question come, your reaction is whether enantiospecific and enantioselective. So I just ask one question to the audience, that if you desire your reaction, what will you desire? It should be enantioselective or enantiospecific? Enantiospecific, because you are getting only 100% of one type of product, that is you need not to separate from the other enantiomers. Okay. So now till here you know that you need asymmetric synthesis, you need pure compound. Why you need? You have an answer, because every isomer may be related to one type of particular activity. So our objective is clear now, that we required pure compound. Now the question is how we can require, what are the methods that which we have to see we can get the enantiomerically pure products. So if you see on your screen, these are general methods. Okay. So if you see, first is resolution of a racemate to chiral compounds with recycling of undesired enantiomer if possible. I will take one by one this reaction. Okay. Second is synthesis of chiral compounds by deriving the chirality from naturally occurring chiral compounds available in chiral pool. Third is microbial or enzymatic transformation, and fourth is catalytic asymmetric synthesis. These are the general methods which are available during your course of reaction. Now what is your course of reaction? You start at synthesis and you see in your substrate chiral moiety is present, you perform any reaction. What is any reaction? आपने asymmetric synthesis का पहला reaction क्या देखा था? You have a aldehyde group, carbonyl group, you are reducing it into alcohol. So this is your general reaction. You perform this reaction and as per theoretical concept, you are getting 50-50 of both the enantiomer. As I said that two doors are available, anybody can come. Now I am giving the lecture, this door has been closed. Now whosoever is coming, he or she is coming from that side. Okay. So what is the meaning of this? One side is blocked, other side is open for the entry. But in start, both sides are open for the entry. So if any reaction you have started and by chance or by theoretical concept you are getting two enantiomers, then we don't have to worry. At least we are getting two enantiomeric products. What we have to do? We have to resolve them. So that is what? That is resolution of enantiomers. So resolution of enantiomers कैसे कर सकते हैं? What is the difference between enantiomer and diastereomers? We are saying that you cannot separate enantiomers, but we can separate the diastereomers. So if you are getting any enantiomer, see in your substrate, what is in substrate? Plus minus denote what? It is a racemic mixture. And what is your target? You want to get pure plus and pure minus, so that you can analyze what type of activity is available with such type of products. So generally what you done? Take the substrate, treat it with pure optically active reagent. That optically active reagent can be plus or minus anything, but that should be a pure enough. So what is the final product? आपके enantiomer में एक chiral unit है, आपने एक reagent में chiral unit लगा दी, तो क्या बन गया? diastereomers. So you can see plus substrate A star minus substrate A star, that means you have a pair of diastereomers. Now you separate them. Diastereomers can be separated by fractional crystallization, distillation, there are different methods. So once you separate them, then you take out the reagent which you have introduced to make as a diastereomer. So you remove the A star, you get your pure plus and pure minus, so you can further use them for the different activity. So this is your resolution. Okay. Now if resolution is the only choice, we don't have to do the asymmetric synthesis, do the reaction, get the racemic mixture, separate them. But is it possible that we can separate them easily? So if I tell you, just give me one example, if you treat acid with alcohol, what is the final product? Ester. If you treat acid with amine, what is the final product? Amides. And if you get back that product, what you have to do? The hydrolysis of ester, hydrolysis of amide. So that means your complementary nature should be there. If you have a ionic salt, amides, ester, in such cases they should be resolved back to the starting substrate. My only query is, if your corresponding A star is not available, then how you are going to resolve it? In your substrate you have a positive and negative isomer, you have to resolve it, that means you have to react it with A star. But if corresponding A star or a reagent is not available, how you are going to resolve them? So if you have a star available which can react with your racemic mixture to prepare the diastereomer, then this method is good. Okay. So even if you get the racemic mixture, choose the appropriate A star, convert them into diastereomer, separate them, remove the A star, you will get your pure enantiomeric products. Okay. But if corresponding A star is not available, then this method cannot be used for the resolving of your racemic mixture. Then resolution cannot be used. Okay. So then we move to the another, that is your chiral pool. What is a chiral pool? Okay. I just want to explain you first reaction, then go to the theoretical concept. Now can you see your target product? That is your enantiomerically pure lactone. What is lactone? The ester unit in a cyclic form, that is your lactone molecule. Can you see ester unit in your final product? And you are able to see the chiral unit. What is the chiral unit? Hydrogen and COH. Hydrogen is your below the plane, COH is your above the plane. Now if I say that enantiomerically pure lactone unit is a part or a molecule which is required for your antiviral drug, then your aspect is that you have to prepare this unit. Okay. Now how this can be occur? See, in starting reaction, starting substrate, that is L-glutamic acid. In L-glutamic acid, can you see the chiral unit? Is it exactly the same which you desire in your product? You see hydrogen and COH, they are present on the same plane which you required in your final product. Okay. So you choose a substrate which have already the desired chirality of your product. Now what you done in this case? You just convert the NH2 to corresponding OH, diazotization, and then you do the cyclization. What is cyclization? Acid react with alcohol to give you what? Esters. Okay. So in this case, if you do this cyclization of OH and COH, you get that cyclic product. Now can you tell me what the chirality which is remain in the substrate directly goes to the product? So what is that thing? That is called chiral pool. The nature has provided us number of molecule which have a chiral unit. Okay. So if such type of chiral unit you required in your product and they are already available in your chiral pool, then just plan a synthesis in a way that unit should be carried as such. Now can you see in this reaction the chiral unit which is present in the substrate that directly move to the product without changing anything. Okay. So what is this method? This is an appropriate chiral precursor from chiral pool can be modified in a series of chemical step to a desired chiral compound. So नेचर से ही आप एक ऐसा सबस्ट्रेट, ऐसा प्रिकर्सर चूज करिए जिसके पास आपकी रिक्वायर्ड डिजायर्ड chirality हो. आप सीरीज और स्टेप ऑफ रिएक्शन परफॉर्म करो उसी सबस्ट्रेट के साथ. पर क्या होना चाहिए? नो स्टीरियोजेनिक सेंटर रिक्वायर्ड इन द डिजायर्ड chiral कंपाउंड शुड बी इन्वॉल्व इन केमिकल ट्रांसफॉर्मेशन. जो सबस्ट्रेट में chiral यूनिट है जिसको आप एज सच प्रोडक्ट में चाहते हो, दैट शुड नॉट बी डिस्टर्ब्ड. तो अगर आप इस रिएक्शन में देखो, स्टार्टिंग सबस्ट्रेट से प्रोडक्ट तक क्या हमने chiral यूनिट को टच किया? जैसे सबस्ट्रेट में थी वही हमारी डिजायरेबिलिटी थी, उसी को हम एज सच फाइनल प्रोडक्ट के लिए लेकर चलेंगे. ओके. सो दैट्स मीन the chemical steps have been involved in a such a way. Why you choose molecule from the chiral precursor? Because you required a particular type of chiral unit. So that chiral unit should not be disturbed at all. It should be directly moved to your final product. So no stereogenic center should be disturbed. नो रेसमाइजेशन शुड बी अलाउड. ऐसा नहीं है कि आपने प्योर chiral कंपाउंड से शुरू किया, स्टेप ऑफ रिएक्शन ऐसे किए, जाके वहां पे फिर रेसमिक प्रोडक्ट बना दिया, फिर उसका क्या फायदा हुआ? फिर हमें उसको दोबारा से किस स्टेप में लेकर जाना पड़ेगा? रेजोल्यूशन. दैट्स मीन a synthesis should be planned in a way your chiral unit should not be disturbed at all. Only chemical transformation should be done. Okay. So however stereogenic center may undergo inversion or retention, but chirality should not be lost. Retention and configuration हो सकती है. आपने SN2 and SN1 reaction पढ़ा होगा. Okay. If you perform a reaction on chirality in SN2, what is the configuration of the product? Inversion. But if you do in SN1, it is racemization. Okay. So then what is the limitation of this method? Only limited number of natural products are available. Only few functional groups are available. Now you start preparing the asymmetric synthesis, synthesis where you get the unequal amount of products. So you first start the method of resolution. अगर उससे पॉसिबिलिटी होगी ठीक है, उससे पॉसिबिलिटी कब नहीं होगी? जब आपके पास कॉम्प्लीमेंट्री ए स्टार अवेलेबल नहीं होगा. सो देन यू मूव टू द chiral pool. अच्छा भाई हम chiral pool में देख लेते हैं, अगर कोई सबस्ट्रेट मिल जाए जिसके पास हमारी डिजायर कायरलिटी हो। तो आपने चेक किया, it is not necessary that always you get your desired chirality in the natural available products, they are very limited. Second, if you get the complementary groups are not present which has to be converted into the unit. अब आप इस reaction में दे, you required OH and COH so that they can condense together to make a cyclic electron. अब आपके स्टार्टिंग सबस्ट्रेट में ये कायरल यूनिट तो प्रेजेंट है लेकिन OH एंड COH ही नहीं प्रेजेंट है, तो फिर साइक्लिक मॉलिक्यूल बनाएंगे कैसे? सो दैट लिमिटेशन कैन आल्सो बी देयर. सो we move to another method, but this is just a list that these chiral starting materials they have been already provided by nature, so it is called chiral pool. Okay, so the question comes, what is chiral pool? It is a list of molecules which has been already available in your nature, which has been extracted from different plants and sources, which can be used for the chemical synthesis of chiral products. So आपके पास अमाइनो एसिड्स हैं, अमाइनो एल्कोहल्स है, हाइड्रोक्सी एसिड है, टर्पीन्स हैं, alkaloids है, carbohydrates है, these are units, they are already present. So you can pick them, you can convert into your target products. So that's mean chirality is already in your substrate. Okay. So we go for resolution, we go for chiral pool. Now we come another method which is enzymatic methods. अभी हमने पढ़ा था enzymes are stereospecific in nature. I will show you one picture which you will explain. First see number 1, number 2, number 3. Just see the substrate, you don't have to remember anything, but you have to just give a picture in your mind. In first case you are doing the hydroxylation across carbon carbon double bond. What is hydroxylation? You are adding OH group across the carbon carbon double bond. Now can you tell me what is the stereochemistry of carbon carbon double bond? It is planar in nature, it is sp2. Okay, so if you are going to add 2 OH group on the 2 carbon of double bond, either the OH group can come from the above, either the group can come from below the plane. So this is your hydroxylation. Now can you see in this example both the OH group are on the upper side, above the plane. You are getting cis diol enantiomeric excess कितनी है इसकी? 100%. That means this is a enantiospecific reaction. You see in second example, what is the difference? At both the carbon double bond क्या difference नजर आ रहा है आपको? सेम ही तो ग्रुप है, COH and H. नीचे कार्बन में आप देखो सेम ही ग्रुप है, H and COH. But when you are getting the product, now can you see the addition of water? One side you are getting OH, other side you are getting hydrogen in the presence of some enzyme, that is fumarase. Okay. Now go to the third reaction. You are seeing 2 carbonyl group. One carbonyl group is part of your ester unit. Okay. Now you are seeing the target product, the enantiomeric excess, you are getting the reduction of 1 carbonyl group where you are getting the OH group. Now can you tell me this OH group is below the plane? If your carbonyl is in the plane, OH can come from the upside, OH can come from the below side, but in your product you are getting the OH from the below side. So in these 3 reactions you are getting enantioselective and enantiospecific products. Now see, if I am saying the cis diol is a molecule which is a synthone for the formation of amoxicillin. Say example, I am saying the product number second, that is the synthone which is used for the formation of medicine dolo. Okay. The product number third is the